This is V. Sujit Babu from ECAB section. Today, my topic is about molecular communication, digital signal processing, microfluidics from ECAB section. From the subject linear IC applications. So, first look onto the quick contents. Introduction, molecular communication fundamentals, principles of molecular communication, chemical reaction mechanisms, microfluidic circuit basics, digital processing molecular system, signal representation and modulation, noise reduction techniques, and signal detection and decoding, chemical reaction based microfluid circuits, design and fabrication methods, reaction kinetics and controls, integration with digital processing, applications and future perspectives, biomedical and environmental uses, challenges and limitations, advance, advances and emerging trends, and finally conclusion. So first look on to the introduction of this topic, molecular communication, digital processing mechanisms. Molecular communication leverages chemical signaling for data transfer in microscale environments. This presentation explores the integration of digital processing techniques with chemical reaction based microfluidic circuits. We highlight fundamental concepts, challenges, and engineering approaches, optimizations at the molecular scales. The molecular scales, molecular communication fundamentals, principles of molecular communications. Molecular communications uses chemical molecules as carriers of information, enabling communication in biological and synthetic systems. It involves molecule emission, propagation through a medium, and reception by a target. Undertaking diffusion, flow dynamics, and molecular interaction is a key for efficient design and operation. So let's look on to the next slide. Chemical reaction mechanisms. Chemical reaction drive signal generation and transformation in molecular communication systems. Reaction controls molecule production, degradation, and conversion, influencing signal strength and timing. Mastering reaction kinetics and pathway design is essential to manipulate communication dynamics and improve reliability. Microfluidic circuit basics. Uh, Microfluidic circuit provides a platform for manipulating chemical signal at the microscale. They consist of channels. They consist of channels and chambers that controls fluid flow and reaction environments precisely. Integration of microfluids enables spatial and temporal regulation of signal transmission for advanced molecular response. Digital signal processing molecular systems, signal representation and modulation, digital signal processing in molecular systems encodes information in chemical signals using modulation techniques such as concentration or molecular release timings. Robust signal representation increases the communication fidelity, aimed noise and interface inherent to molecular channels. Noise reduction techniques. Noise in molecular communication arises from random molecular motion and environmental fluctuations. Signal processing approaches like filtering and error correction migrate noise effects, enhancing detection accuracy and system robustness in complex biochemical environment. Signal detection and decoding. Effective signal detection and decoding are crucial for interpreting molecular communication signals. Techniques involves chemical sensors but that identifies molecular concentrations and temporal patterns. Advanced algorithms that decode these signals to retrieve the transport information accurately, overcoming noise and distortion in dynamic microenvironments. Chemical reaction based microfluidic circuits design and fabrication methods. Designing microfluidic circuits requires precise control of channel geometry and materials to same predictable fluid and molecular behavior. Fabrication involves techniques like soft lithography and 3D printing. Optimal design balances reaction efficiently. Single transmission and integration with downstream digital processing components. Reaction kinetics and controls. Controlling reaction kinetics in microfluidic circuits is essential to regulate signal timing and intensity. Parameters such as reactant concentration, temperature, and catalyst presence influence reaction rates. Fine tuning these conditions enables desired communication protocols and system responsiveness. Integration with digital processing. Integration microfluidic circuit with digital signal processing systems enhances overall molecular system performance. The integration allows the real-time feedback, signal modulation, and adapt control, leading to improved accuracy and functional versatility in complex environments. Applications and future perspective. Biomedical environmental uses. Molecular communication systems find applications in targeted drug delivery, biosensing, and environmental monitoring. Their ability to operate in confined spaces and biological environments opens possibilities for personalized medicine, pollution detection, and tab on a chip devices. Challenges and limitations. Current challenges include signal interface, limited data rates, and scalability issues, and microfluidic fabrication and variability in biological environments also pose significant hurdles. Addressing this is vital for practical adoption and development. Advances and emerging trends. Recent advances focus on enhancing modulation schemes, improving reaction control, and integration. AI-driven processing emerging include hybrid communication systems and novel materials for better system stability and efficiency. This promotes accuracy to accelerate field growth And finally, let's come to the conclusion. Molecular communication via chemical reaction based microfluidic circuits offers a promising approach for microscale data transmission. Combining precise reaction control with digital signal processing enables robust adaptability communication systems. Despite current challenges, ongoing research and technological advances passing the way of impactful world applications across biomedical and environmental sciences. Thank you.